Thank you very much, Hans Martin. Thank you very much for the introduction. So that's very nice. So hello, everyone. So I hope you're having a good morning or afternoon or evening. Greetings from my very warm office in Gothenburg. So thank you very much to the AIRE organizers for inviting me to give this talk. I think it's a really great opportunity to give some updates on what we've been working on and to start some dialogue and to have some interesting conversations. So of course, I'll be talking about requirements engineering for machine learning, and I had to have kind of a catchy title. So non-functional requirements as core functions. As always, I probably have too many slides, but I'll do my best to edit myself and stop on time so that we have some time to discuss and ask questions and things like that. I think that's the most interesting part. And if there's any problems with the sound or the subtitles, just let me know. Okay, so I have the obligatory kind of starting slide where I talk about the rise of machine learning. I think we see a lot of these slides, so it gets a little bit tedious, but I wanted to, of course, make the point that machine learning is becoming more pervasive and you're more likely to encounter it. So what I really wanted to report is I'm really curious what percentage of software in use today uses some form of machine learning. And I don't necessarily mean like what percentage implements the algorithm, but what, how many of all the software out there, all the software systems, like what percentage uses machine learning. As a spoiler, I wasn't actually able to find this number after some digging. If you have this number, then please feel free to share. I think that's really interesting. But what you can find if you look at machine learning and the rise of machine learning is a lot of more business-oriented statistics. So I found, for example, one that looked fairly legit. So, for example, we see like a 14% increase in global gross domestic product by 2030 with the advances of machine learning and AI. More C-level executives using machine learning as part of their business. Budgets for machine learning programs are growing, and 91.5% of leading businesses have ongoing investments in AI. So we can see a lot of these more sort of business-oriented statistics that really show us that this is becoming a more pervasive thing. And so, why is that relevant to us? What are some challenges that the rise of AI and machine learning specifically raise for requirements engineering? And so I'll just outline a few selected ones here, and we've seen some good ones already in the talks earlier today. But the software machine learning has new characteristics, and I really put new here in quotes because these aren't really new. It's just that they're not necessarily as so pervasive. So this type of software has a level of uncertainty or non-determinism. So we can't always say that, if it receives output A, B is going to happen. And also we have incomplete specifications. So because it has uncertainty and non-determinism, we can't really say all of the things that it's going to do. So we can't fully specify upfront what the system will do. And so again, new, because of course, uncertainty and incompleteness have been research topics in requirements engineering for a long time. It's just that most solutions assume sort of a certainty and some level of completeness. So can our sets of concepts and methods, our long history of requirements engineering be applied in these cases? And if it can be applied, is it just this regular old system, no adjustments needed? Do we need adjustments? Do we need extensions? Or are our techniques and tools and concepts just not really applicable at all? Do we need all new approaches? So it's a very broad question. I mean, the answer, of course, depends very much on the context. And also the processes and methods are different. And I'll talk a little bit more about that later with a specific case study. So we've been dealing for years now with agile requirements engineering. And, most of the companies that we work with and we've been collaborating with are using some form of agile, often scaled agile like SAFe. And that already raised quite a lot of interesting issues for requirements engineering. So now these same companies that have been going agile are now starting to use machine learning. So we have a lot of new processes and a lot of complexity here. And then one of the focuses of this talk is, non-functional requirements. I argue that they've always been important, but now they're even more important. But are they the same? Are they the same types of NFRs? Or do we need new ones? Do we need new definitions? Can we reuse some of our old definitions? Can we reuse measurements? Do we need new measurements? And of course, this is all complicated by the fact that our NFR solution wasn't complete. It's not like we had this totally figured out for systems without machine learning. It was still an open, difficult problem even before the arrival of machine learning. So that's some challenges. And of course, there's lots more. So what I'm going to talk about today is I'm going to talk a little bit about the state of the art of requirements engineering for machine learning. And then I'm going to talk about a specific line of work here we're doing with a PhD student, Habib, NFRs for machine learning. And then I'll talk about a case study that we just completed on perception systems and autonomous driving with some colleagues, many of whom are here. A little bit of a summary, and then talk about future work. So a little bit of the state of the art, and I say partial view because this isn't as a result of a systematic literature review. This is just especially focusing on papers that happen to have been in RE or AIRE. And of course, the 3 papers we just saw should be included here and are not. And in fact, the first paper we saw today did a really nice job of overviewing the state of the art in RE for AI. So that means that I can speak less about this. So we have a number of different papers on problem exploration. So for example, interviewing data sciences, or providing an RE for AI taxonomy with some of the challenges that I mentioned before with more detail, looking at NFRs, some of my previous work, which I'll talk about more later. And then there was a systematic mapping study that came out last year covering 35 studies, looking at the topics, the NFRs covered, the paper types, etc. So that's also very useful. So this is sort of problem exploration and overview. And then there are some solutions focusing on RE for AI. So there are some solutions having to do with ontology. So getting into a more sort of formal ontological definition of the concepts that the machine learning model uses, focusing specifically on robustness, for example. There's quite a few different works looking at quality like we're looking at. So a taxonomy of NFRs, quality assurance for AI, extending the quality characteristics defined by ISO. There's some very prominent work about safety. So AMLAS is looking at assurance for machine learning and autonomous systems. And then there's a lot of work that looks at modeling. So there's quite a few different sort of I-star or goal model type extensions, extending it to think about machine learning concepts. So this is just a very quick overview of some of the state of the art. And I think what I want to kind of portray here is that although this is an upcoming area with a lot of really great work, it's still very incomplete. I think we still don't necessarily have a common understanding of the problem. And although there's some great solutions in specific facets or areas, it's still very much a work in progress for everyone. And so a sample view from outside of requirements engineering. So I'm just focusing on some of the RE for AI papers or RE for machine learning papers. But of course, there's also a big area of work now that's software engineering for AI and machine learning. And so you can see associated with ICSE, they had, some nice workshops, etc. So a quote from some of my colleagues here who are software engineers, but not really requirements engineers. So in addition to having development teams executing on requirements specified by product management, the development of software systems is progressing towards a data-driven practice where teams receive an outcome to realize and where design decisions are taken based on continuous collection and analysis of data. So this is just a nice summary of kind of this table here. So according to these, fairly prominent authors, you have 3 types of systems or 3 types of development approaches. There's requirements-driven development, there's outcome or data-driven development, and there's AI-driven development. And you notice there's that sort of strict divide there. So, if you read between the lines here, you can see, even though this is outcome data-driven development, I mean, we as requirements engineers would say that these quantitative targets are actually requirements. They're actually, quantitative NFRs, but that's maybe not kind of the viewpoint here. And I would also argue that there's some requirements down here too. So even though this is the AI-driven development, I mean, that doesn't mean that requirements engineering doesn't necessarily play a role. So according kind of to the outside view, at least this particular view, we are here, but I think we should also be seen to be here. So this is the idea. But one could be kind of, play the devil's advocate and say, why? I mean, if these types of systems are working well, if they're functional, if there's no problems without us, like, why do they need RE? So, why are we needed for these other types of systems? And so we want to make sure it's, we don't have a situation like this where we have RE, left out in the cold when, the fields of machine learning, AI, software engineering, and data science get together and progress. And so we can think a little bit of going back to basics. So I thought about, okay, what do I tell my students when I teach them? Why are we doing requirements engineering? Why are they in this course? And I should say that I teach first semester students. So these are some really basic reasons. We're losing some nuance and complexity here. And then, do these reasons still hold for ML-based systems? Like, should we actually really be in these bottom 2 rows? So I tell my students, let me just click here, that we avoid, or we perform and conduct requirements engineering practices and concepts to avoid wasting time coding something that won't be successful. But for ML-based systems, I mean, yeah, this is also the case, but experimentation is inevitable in machine learning. So it's really rare or difficult to upfront specify exactly what it should do and then have it done. So there's a lot of experimentation, there's a lot of iteration, and I think that's unavoidable. But maybe that doesn't necessarily mean that, you know, we don't need requirements. Maybe we can use requirements to try and make the targets clearer and maybe to mitigate some of this iteration and experimentation. So I tell the students that we want RE to avoid having to make many changes, but, you know, drift in machine learning and enabled systems, I think, is inevitable. Like, even if you make a really good system, over time, the data will change, things must be retrained. But again, maybe requirements can be help here to monitor and manage this sort of drift and this change. To make the final product better, I mean, yes. I mean, so if we have clear quality and functional requirements, we certainly hope that the final product would be better. To anticipate the effects of your product software, I mean, yes. And I think here we even more so need to anticipate the effects, and maybe some of the same techniques would work. So here I'm thinking, you know, ecosystem modeling, maybe I-star modeling, the sorts of things that try and understand like how the system would work in the world and what sort of effects it would have. So some of our ethical techniques, for example, like we just heard. To avoid being sued, so yes, this is very relevant. In fact, it's even more relevant. So here we have a very complex rule of safety and standardizations that is very much a work in progress. And also some further reasons, so internal communication. So we use requirements for this. So yes, this is still very much needed, but our current representation is working. When you're talking about machine learning related communications, you really want to pass around like the system shell specifications or user stories. And finally, organizational memory. And so, yes, this is still very relevant, but what in these types of systems do we need to remember? And is it different than the regular types of systems? So this is a lot of very broad questions. And of course, you know, like a good talk, I'm not going to answer all of them. In fact, I'm not sure I'm going to answer many of them at all. So we're focusing on a subset of this. But what I'm really trying to convince myself is that there is a place in machine learning development and systems using machine learning for requirements engineering and for requirements analysts. And so I hope so. I think that's the case. So I'm going to get into one of the subtopics here. So the first subtopic I'm going to look at is NFRs for machine learning, so non-functional requirements for machine learning. So here, this is a funded project from the Swedish Research Council, lasting several years. And again, we have many interesting questions and not so many answers yet. And so this is work with PhD student Habib, who is here, and also co-supervised by Gregory Gay. And so if we think of, you know, qualities of machine learning solutions, I mean, this is something that comes up, and again, we heard about this morning. So accuracy and performance, of course, correctness, fairness, transparency, security and privacy, still very relevant, testability, reliability, other things, maybe trainability, maybe, you know, old sort of familiar NFRs like maintainability. So there's lots of different qualities of machine learning solutions. And some of these are very familiar, and some of these are, you know, relatively new. And maybe others go out of focus. That's some of the things we're trying to kind of look at here. And so I grabbed a quote from one of the sort of SE for machine learning type papers. So instead of functional requirements in non-ML software systems, quantitative measures comprise the majority of requirements for machine learning systems. So what we're really seeing here is that in these machine learning enabled systems or machine learning containing systems, NFR or non-functional requirements are really some of the prominent requirements. It's not so much what the system does, but how well it does it. And it's so much so, in fact, that if you try and have a conversation with about non-functional requirements with people working in machine learning in industry, sometimes, you know, they're a little bit confused because for them, those are the requirements, like that, those are the functional requirements. So here our terminology starts to break down a little bit, at least in our industrial context. So what we've done so far is an interview study, which was already published in RE'22. So I'll talk a little bit about that, but not too much. We followed up with a larger survey, and I'll talk a little bit more about that. And then we started to work on a high-level SLR, and I'll talk a little bit about our initial progress there. And then the solution stage is still a work in progress. So just as a little bit of kind of background and context to one of the things we're exploring here. So you've probably seen this picture. So this was Scully et al. Several years ago. And that's not really what this paper was about, but they had this really nice diagram here that basically shows that, you know, even though machine learning is becoming more prominent, this is why I keep saying like machine learning enabled systems or systems with machine learning. The actual machine learning code is only a small part of a larger complex system. So when we talk about requirements or non-functional requirements for machine learning, which piece are we talking about? Are we talking about the whole system, just the machine learning, the data? And so in one of our recent workshop papers, we had this image. So we're thinking of the different possible NFR scopes. So you can talk about NFRs over the whole system. You can talk about it just over the model, over just the algorithm, over the other code, over the results, over the data, over the training data, over the runtime data. And this scope, or this sort of, what I want to call it, context, but the object that the NFR is applied to actually potentially makes a difference. It may mean a different meaning NFR, a different measurement, etc. And so this is something very complicated that we're only just very beginning to explore. So back to the interview then, Habib interviewed 10 participants with industrial ML experience. We asked them questions like, which NFRs are more important to you? Over what aspects do you measure them and define them as per the last slide? What challenges are important, etc. So briefly, this figure, it basically lists all the NFRs mentioned in the interviews. And so the top kind of two chunks are the important NFRs, and the bottom one is the less important NFRs. So you can see right away, there's lots of important NFRs and not so many less important NFRs. And in fact, this yellow color means that it was mentioned in both categories. So even the NFRs that are mentioned as less important, we have some conflicts. Some people said, for example, usability is less important. Other people said, no, usability is actually quite important. And it came up quite a lot. And so, this is basically just an idea of what NFRs are people looking at in machine learning systems. So things like accuracy, reliability, usability, explainability, testability, maintainability, etc. And then it really kind of bringing forth the idea that not only do we have new NFRs that we haven't necessarily considered so much in the long history of requirements engineering, but even some of the older NFRs like usability, flexibility, etc., are still important. They don't go away. And that makes sense. If machine learning is part of a larger software system, all of the NFRs we've cared about are still very relevant. So we extended this work with a survey. So we used our interview findings to create a survey kind of confirming and exploring some of these findings. So we had 42 at least partial responses. We were kind of aiming the survey more at industrial participants, but these are really busy people. So in the end, what we got is a mix of industry and academic respondents, but this allowed us to be able to compare the answers between these two different groups. And in fact, what we noticed in our interviews is that sort of this line between, I work in industry, I work in academia, in the world of machine learning and AI is a bit more blurry. So a lot of the people working in industry have, kind of stronger ties to university, and the people working in university maybe have stronger ties in industry. That's just our kind of informal observation here. So making that strict cutoff is not so easy. So we asked them a general question. So do NFRs play an important role in ensuring the quality of an ML-enabled system? And then is there a difference in how these NFRs are defined and measured between traditional systems and ML-enabled systems? And you can see here, so blue is strongly agree and orange is agree, and then trailing off. So generally, almost everyone agreed that NFRs are important. And most people also agreed that there's a difference in how NFRs are defined and measured between these machine learning systems and not machine learning systems. So we also gave them the list of challenges elicited from the interviews and asked them these challenges. So which is the most important to you? Or, well, they're not really ranking them. We've asked them whether they agreed or disagreed, and then we've ranked them based on the kind of level of agreement. But you can see here, there's not a huge difference. And I think actually the one with the strongest agreement is at the bottom. So for example, they strongly agreed, and most of them agreed, so almost everyone agreed that domain dependency of NFRs is a challenge. Also generally agreed that missing measurement baselines is a challenge. Implementing rigorous testing is a challenge. Lack of awareness among customers is a challenge. Uncertainty is a challenge, and lack of awareness among engineers is a challenge. So overall, we more or less confirmed some of our challenges. Not everyone agreed, but most people agreed that these were challenges. But interestingly, and kind of a little bit of a conflicting result, we also asked them, how often do you come across these challenges? And orange here is in a small percentage of projects, and blue is never. So they do come across these challenges, but actually fairly often they don't. And then in other times they do, but not very often. So they agree that NFRs are important, and they agree that these challenges exist, but they're not necessarily finding these challenges in all projects. That's kind of how you interpret these results. So one of the possible reasons for this could be, again, this terminological interference. So again, what we would define as an NFR challenge, they would just say it's just a regular machine learning challenge. Like if they're dealing with performance, that's just machine learning. So this could be a little bit of a different mindset here, or it could just be that these challenges maybe aren't super pervasive. So we also in this survey asked them to kind of rank the NFRs. So, depending on your experience and expertise, which NFRs are the most important. So you have blue, very important, orange, medium, high important, and onwards. And so from this, we could rank them. So for example, like accuracy, again, performance accuracy is right up there, integrity, reliability, security, safety, and other things are lower. So at the bottom, we have usability, maintainability, etc. So this kind of, gives a little bit of indication, at least amongst our respondents, what they're really focusing on. It's interesting that fairness here is it's kind of not at the bottom, but it's the middle bottom. So fairness is, important for them, but at least it wasn't super important. And also transparency is somewhere in the middle. Whereas as you see, these are quite often very prominent focuses, or at least I think that they're very prominent focus in academia. Trust is towards the top, traceability is towards the top. Some of this, of course, could be the domain. So in the interviews, our participants were from a wide variety of domains, and in the survey, they were also from a wide variety of domains, but we didn't necessarily have data that supported us kind of dividing these results as per domain. But I do think domain would make a difference. So if you're asking someone from automotive versus healthcare versus business, this ranking would change. But sadly, we don't really have good data to kind of do that type of comparison. We did, however, have the data to do the comparison between academic versus industrial backgrounds. And so we actually, I'm showing two figures here, but we actually had a third category where people said, yeah, I'm both. But you can see here that this ranking differs a little bit depending on whether you're in industry or whether you're in university or academic in some way. So, accuracy and reliability are still at the top, but now fairness is at the bottom in industry, which is kind of interesting, and transparency and usability are still down there. Security raises a little bit higher, and when you're talking about the academic positions, safety is quite high, whereas safety is in the middle. So there's some subtle differences here. So there are, there's a few things that stand out, but more or less we can say that the ranking depends a little bit on your background. So just to summarize some of these results, and I've kind of given you a whirlwind tour. So the RE paper is out, you can read it, and hopefully the other results will be published soon enough. They've been submitted. So most of our participants agreed that NFRs are important in ensuring machine learning quality, and that there are differences in traditional systems and machine learning enabled systems. Accuracy, reliability, integrity, and security are particularly important for machine learning systems. Most NFRs for traditional software is still relevant. A few become a little bit less relevant. And then there's other NFRs where there's sort of conflicting views. So the perception on the importance of efficiency, fairness, flexibility, etc., are split. So some people say, yes, this is very important. Other people say, no, it's less important. Most practitioners focused on defining NFRs over the whole system or sometimes on the models, but few of them considered defining NFRs over data specifically. And then, of course, there's a number of challenges we found, and we managed to kind of confirm the relevance of those challenges through the survey results. So moving on to the next part of this NFR for machine learning work. So what we've basically looked at this point is sort of, we wanted to know, what's happening in industry? How are people treating NFRs? Is this something that comes up for them? Is it an important problem? How do they define them, etc.? So we want to ask a similar question looking more at from the academic side. So here we were looking more at the traditional systematic mapping and systematic literature reviews. So what is the perception and treatment of NFRs for machine learning in academia? And of course, the reason to ask both these questions is eventually we want to compare across to see, oh, industry is focusing on this, but academia is focusing on this. It's the same, it's different, etc. So this is all fine and good, but this is way too big for one systematic literature review. So you've seen, like in this table we have, I didn't count, but like 15, 20 NFRs. So you can't do an SLR or a systematic mapping study over that many NFRs for machine learning. It's huge. So what we did is try to perform an initial mapping study to estimate the number of relevant papers on machine learning for each NFR. And the idea here is that we wanted to kind of, find the ones that had a lot of focus and kind of leave those out, not because they're not interesting, but because those could be mapping studies on their own, and focus on some of the less investigated, sort of less prominent NFRs in the literature. So what we did, 3 of us, we took the top 50 or 100 papers from Scopus results, and then we classified them as in or out of scope. And so we searched for, machine learning and various synonyms, machine learning, deep learning, etc., requirements engineering, and then the specific NFR. So we had that same search string plus efficiency, plus fairness, plus maintainability. And then we also ended up doing sort of a clustering of NFRs, because we found this was easier to kind of sort and understand the results if we can kind of take all this list of NFRs and cluster the related NFRs together. So this is what we came up for clustering, and this was published earlier this year in an ICSI related workshop, if you're curious to see these details. And so cluster 1 is kind of everything about accuracy and reliability and things like that. Cluster 2 is more about explainability, transparency. 3 is more about ethics and fairness. 4 is more about efficiency and performance. 5, adaptability, flexibility. 6, privacy, safety, trust. And then 7 is everything left over which did not fit in the previous 6 clusters. So there were a lot of things that, were kind of unique and didn't fit with these things. And so I should say that this was, the clusters that we made based on our knowledge reading many, many, many abstracts. But of course, this is subjective. So you could make an argument that this one should actually be in this cluster and this one should be in that cluster. So this is, something to help us, but we're not necessarily claiming that this is the answer. There's different ways you can do this. So what we end up doing, and I'll explain kind of briefly this big ugly table. So here we have all of our NFRs that we focused on, which cluster they come from, and then the initial Scopus search results as of, I think it was last fall, so it's a little bit dated even at this point. So for example, if you search for performance plus requirements engineering plus machine learning plus deep learning, et cetera, you get like 12,000 results. And so we're not doing systematic literature review on performance, that's right out. So what we tried to do is estimate of these search results, how many were actually relevant. And so again, we took the top 50, or in some cases the top 100, and went through and determined whether they're in or out. And then we did some intercoder reliability with FISIS kappa between the 3 of us coders. And you could see the kappa scores here. Some of them are okay, like, 0.7 is good, 0.5 is okay, 0.4, it's kind of borderline, but some of them are really awful, like 0.3, 0.2. So some of these NFRs are easier to classify, at least to classify the relevance of the papers than others. And so from this, like you can say, like in the, basically, in the 50 papers, we'd say like 20 papers are in, and there from that, you can extrapolate to say how many relevant papers might be there. So for example, we think there's probably something like 600 relevant papers for NFRs and usability. So, or for machine learning and usability, maybe about 980 for fairness, maybe 600 for explainability. And this is just a rough estimate. And so this will help us and maybe other people kind of move forward and understand, where to focus our mapping studies on. And so we're kind of focusing more towards the bottom here. We did one final thing as part of this study. So you've seen this figure before. So this NFR scope. And so what we tried to do is try to understand which of these NFRs was relevant for which of these pieces of the system. And so we made kind of an initial table. Now, I should say I'm not super happy with this table, because even if I go back now, looking at what the 3 of us did several months ago, it's hard to kind of understand and remember. But the general point I think I want to make here is that I think what we need is to consider each NFR over each part of the system. And for each of these parts, we need to say, is this relevant? How do you define it? And how do you measure it? And so what we tried to do here is say, for example, like repeatability. Does repeatability apply to the training data? Like, does it make sense to talk about repeatability of data or repeatability of the algorithm or model? Maybe not, but maybe it does make sense to talk about repeatability of results or of the whole system. But even there, you can see that's kind of like, well, it depends. So this was kind of our initial crack at it, but I think it's very subjective. And I think what we really need is for every single box inside of this table, we need a definition. And you could see that that's not actually a very trivial thing to do. So, earlier today we had the definitions of transparency versus, what was the other one? Transparency versus explainability. They're not quite the same thing. There's some subtle differences. And so this could be, you know, work of lots of different people, but this is, I think, something we're interested in doing for some example NFRs. So to go a little bit deeper and understand how the definition changes depending on the type of system, or as Alessio asked earlier, maybe the definition also changes depending on the type of machine learning solution. I hope that we can be at a higher level of our definitions that it doesn't, but maybe it does. So this is something we have to explore. So that was all about our problem exploration so far, and now we need to work towards solutions. So I'd like to come up with, Habib, you know, something that is lightweight, business friendly, and intuitive, which maybe conflicts with it being publishable. We'll have to see. So maybe, you know, NFR templates, models. We can take inspiration from existing work. So for example, there's a Cooper model, which looks at kind of the utility and differentiation breakpoints of NFRs. There's AMLAS, as I mentioned, that looks at how to go about having a safe machine learning system. So maybe that could apply to other NFRs. There's the Bosch et al. Various stairways. There's stairways everywhere. But these types of stairways, I think, are really easily adopted in industry. So industry really likes these kind of, you know, conceptual views of how to actually, you know, the different stages of adoption. So maybe there's different stages of adoptions or of considerations for NFRs. So these are just some high level ideas. It's very much still a work in progress. So that's the first topic. And I think we'll start with the second one, and I'll try and cut myself off if I go too far out of time here. So just actually let me remind myself here. So yeah, 30 minutes. Okay. So we also recently ended a case study on perception systems and autonomous driving. And so this was also a funded pre-study from the Vinnova agency in Sweden. And so this study I worked in as part of a large group with quite a few different people. And of course, you can see some very familiar names here. And I think at least 3 of them are in the workshop, or at least last time I checked. And so this was with partners in RISE and some companies, Anatel and Zensact, and the University of Gothenburg. So what we were doing here was we did a lot of different group and individual interviews with relevant company personnel and all the various tiers of autonomous driving, mainly in Sweden. We did, you know, purposive, convenient, and snowball sampling, 19 participants from 5 companies. We did group thematic coding, a lot of effort, actually. We spent a lot of time coding this stuff as a group. We had lots of transcripts. And then we did a follow-up workshop where we presented our themes to the invited partners and had a discussion, and we're currently writing up results. So a little bit of background. So we were specifically talking to people who looked at perception systems, and this is just a high-level model that we used in the interviews to kind of ground what we mean by perception systems. So we have the general sense, plan, act framework, sensors. Senses is happening in terms of various sensors like radar and LiDAR. And then this contributes to perception, where you do obstacle detection, etc. It contributes to some sort of planning, you do route planning, and then some sort of action in an autonomous vehicle. So we also use this kind of high-level model to try and summarize the purpose of this study. So what we were really kind of looking at is, you know, whether quality at one stage could be used to create quality requirements at a different stage. So here you have kind of at the top all the way on the right, the quality of the function. So the function could be like, you know, parking assistance or you know, like automatic braking or steering or some sort of, you know, real function in a car. And then there's the perception correctness, so the actual, you know, correctness of perceptions in the images, the accuracy of the machine learning model, the preciseness of the annotation over the data, and then the data quality itself. So in each of these various levels, we can talk about quality requirements or non-functional requirements. The question is, how do these NFRs or quality requirements relate on these different pieces? So like, could you take a specific quality target in a function and say that because we have this quality target, we know that we need this level of annotation precision, and we know we need this level of data quality, and we know we need this level of model accuracy, etc. So that was sort of one of the driving questions of the study. Okay, and so I'm just going to very briefly summarize some of our results, because the results are big. And again, we're writing them up, so I hope that you can read them, you know, probably later this year. So we identified 8 major themes when we're doing our qualitative coding. So data, perception, artificial intelligence, machine learning concerns, system and software engineering, quality, ecosystems, requirements engineering, and annotation. And for brevity, I'm going to focus a little bit on quality, but I'm also going to focus a lot on this requirements engineering topic, because I thought some really interesting things came up here. So this is an overview of our high-level codes for the requirements engineering sub-theme. So we had some codes having to do with breakdown, documentation, ways of working, scenarios, operational context and scope, and tracing and change. So what are some of the, in my opinion, some of the most interesting things we found here? And my colleagues, my co-authors here might disagree on what is the most interesting, but these are the things that stood out to me. So, I mean, ways of working, they don't follow the traditional form of requirements engineering. I mean, who does? I mean, some people maybe do, but what is the traditional form of requirements engineering? I realize it's kind of a vague statement, but what I mean is that, you know, we talk to a lot of these companies independent of machine learning, and most of them are going through some sort of agile transition. So maybe they used to work in a more top-down V model type way, and now they're becoming more agile and typically working with frameworks like SAFe. And so they're not even necessarily doing those things when they get to the machine learning part of the system. So they are still in other parts of the system, but there's kind of a cutoff. So they work in a kind of a more traditional systematic way, and then they get to the machine learning part, and there's kind of a bridge or a gap. So specifications, so much on specifications. I thought we found a lot of interesting things here. So they don't necessarily have one. That's the interesting thing. So, I mean, we asked about this a lot. We kept trying to ask, you know, like, how do you write it down? Like, what form is it in? And I don't think we got super clear answers from everyone, but they don't really have traditional requirement specifications for the machine learning components. At least they don't have large specifications. So they may have a rough specification. They may have some high level requirements. They may have some high level functional requirements. But the requirements that they do have, sometimes they're not really a big fan of. So sometimes these requirements may have unclear origins, and they're not really sure if the setter of the requirements understands the impact on the machine learning results. So here we see some different spaces of knowledge sometimes between the person that does set the few requirements that they do have and the people that need to make it actually happen. So sometimes these requirements given are not actually feasible with the data that they have, or they're just not realistic. So they don't have necessarily a kind of a full traditional requirement specification for the machine learning system or the machine learning part of the system, but they do have a specification for data annotation. So this terminology of specification came up a lot for annotation. So they have a way to describe how the data and how the images in this case should be annotated. They also have some data specifications. So here, this kind of resembles the ontological work that I mentioned many slides ago. So they need to understand, you know, exactly what is a pedestrian, what is a crosswalk, et cetera. So what are the classes? What is the data distribution? What is the quality, et cetera? And they do still have some specifications kind of, you know, on the edges, on external hardware, sensors, et cetera. And for them, to a certain extent, data is the requirements. So, I mean, they don't necessarily have a full specification because the data acts as a specification to a certain extent. So we also had, you know, interesting things about breakdown. So they don't really do requirements breakdown in a traditional sense, or again, what is traditional, but there is some sort of, you know, form of more typical breakdown until you get to the machine learning system. And then it's maybe more of a trickle down. So they don't necessarily do a kind of any sort of formal decomposition or refinement. They have rough requirements, and then they deal with scenarios and expectation and experimentation to try and make these requirements happen. So I like this quote that we got, trickle down. It's less of a breakdown, less of a refinement, and more of a trickle down. They also talked a lot about requirements allocation. So deciding like what piece of the system satisfies this requirement. So, you know, is this allocated to the sensors, the algorithm, or is this something that, you know, we deal with in a very redundant way? Is it hardware? Is it software? Is it machine learning? Requirements on data showed up, on sensors and on functions, etc. And also, of course, requirements in other parties. There's a very complex ecosystem. So they may talk about requirements on other tiers in the ecosystem. And so one thing that came up a lot in these interviews was scenarios. And I thought this was really interesting because, of course, scenarios is a topic that's been around in requirements engineering for a long time. And, you know, it's not that they disappeared. It's just maybe we were more interested in user stories and things like that. But they independently, you know, without us prompting them or putting this word in their mouth, talked a lot about scenarios. For them, it seems to be a very intuitive and natural way to represent requirements for machine learning. Because you can't really say everything that the system will do, but you can say what it does or what it should do in specific situations. So that's very important. Edge cases came up as very important. So you want to talk about scenarios that cover not just the common cases, but the uncommon cases. So we had a great example where, you know, a car was driving at night and it was following along two bikes with the lights on, but the bikes were at a distance apart from each other that looked like another car. So that's very much an edge case. That's not going to happen very often, but the system should account for these sorts of edge cases. And so that's very interesting. So they have thousands of scenarios, and they look at distribution based on the real world, and also try and find these edge cases. And these scenarios drive development. And we also came up to this ODD, this operational design, I'm missing the last D, operational design description. Yes, that's it. So that's very much, I think, an automotive term, but this is kind of what we would call context. So a little bit different than a scenario, but it's more like, is it raining? Are you in Sweden? Is it night? Are you in Italy? These sorts of things. And this is also very important for the systems and related to scenarios, but not quite the same thing. So very important concept for them. So a little bit about quality or NFRs. This also came up in the interviews. So when we were analyzing what they said, we kind of divided this between model, system, function, and safety is a whole different thing. So at the model level, they did talk about performance, correctness, accuracy, efficiency. At the system level, performance, robustness, comfort. At the function level, performance, accuracy, suitability. But you can see here that the types of requirements and non-functional requirements they talk about at each of these levels does differ a little bit. So performance is everywhere, but you can talk about the suitability of the function. You don't necessarily talk about the suitability of the system or the suitability of the model. I mean, maybe, but that didn't come up. And safety for them is a huge deal. So this is a big problem and a big issue, or at least it's something that came up a lot. I mean, this was also one of the topics of our study. But how to ensure safety, and specifically, how do you work with current safety standards? And there are some new standards that are evolving to try and address AI and machine learning, but it's a difficult problem. And robustness actually was another one I should mention that came up with a lot. That was a very important NFR for them. So how to make things redundant and robust. I thought this was an interesting quote. So most of our development is an iterative process, and it's not more about literally how to achieve a certain goal. It's more about how to avoid certain error. So it's less about specifying all the system things the system should do, and it's more about saying what the system should not do. Like we should not hit a pedestrian, for example. And they talked a little bit about trade-offs. So we asked them about trade-offs, and they could give us some answers, mostly like safety versus some other non-functional requirement. But for them, it wasn't something that seemed to come up a lot. So that's not something that they think about explicitly a lot, trading off between these different NFRs. Okay, so begin summarizing and moving towards the end. So, I mean, at the beginning, I'm motivated by saying we were looking for kind of quality links between these different pieces of this autonomous driving system, and we didn't really find them. There's no kind of clear quantitative links between the quality of features, models, data, annotations. So you can't say, because I need this quality here, therefore I need this quality here. They are linked for sure, but I mean, they're just not linked in a very formal way. So this kind of idea of trickling down, I think, is relevant here. So because we don't really know how they're linked, of course, there's a lot of experimentation here. So traditional RE methods are only followed to a certain point, and I mean, I'm even including now Agile and traditional. That's how far we're moving now. Agile is traditional. So you use these types of things up to the boundary, when you're at the feature level, but once you get to the part where you bring in the ML, now you kind of just give up on that a little bit, and it's more about negotiation, experimentation, and this trickle. Safety and standards are a key and challenging issue. You have requirements represented as data. You do have requirements over data and annotations, and you have requirements as scenarios, and you do have some requirements as requirements. So they do have some high level sort of incomplete requirements or requirements to sensors, to components, to external parties, etc. But there isn't necessarily like one specification for the whole system. So we're kind of abandoning the notion of complete and correct requirement specification for machine learning subparts. But that doesn't mean that, we're not needed. So requirements do play a role, even if they don't always call them that. It's just that it's a little bit of a different role than we would kind of traditionally think in a top-down way. Okay, I'm almost ending. So what have I talked about? So I talked a little bit about, state of the art and a sample view from outside requirements engineering. So we want to make sure, not to be left in the cold, not just for our own self-preservation, but because, I genuinely think the reasons why we've been doing requirements engineering for decades still applies very well to machine learning. It applies a little bit differently, but it applies very well. So we talked a little bit about some of the interview results and the theme and codes of Habib's work, and then some of these survey results, ranking NFRs and comparing between different groups. A little bit about the scope of definition for NFRs over machine learning, about some of these clusters and the systematic literature review that we only just barely started. It was a lot of work actually, but you can see like it's not even a proper systematic literature review yet. It's just too big of an area. getting into this case study for perception systems, and then, you know, some of the key findings in terms of how requirements engineering works in this context. So this is what I've talked about. So our future work, so we have all these like an epic amount of qualitative results from this case study. And so we're currently working with Habib and the rest of the partners to publish this, and I hope you can see it soon. We want to finish a focus subset of this SLR to pick a few different NFRs and continue this work. You know, and design and evaluate NFRs for machine learning solutions. So move towards solution space. And also I'm particularly interested in processes and methods for RE and machine learning. So, you know, how do you kind of bridge that gap from its traditional requirements engineering and then suddenly it's not? I think that's really interesting. So that's our future work. What is your future work? I'm very curious to see, you know, how this fits with all of the great work I see in the community. And so I hope I left some time for that. And that's me. So thank you very much.